Now let's look at the example of isothermal compression of an ideal gas. Now I have used the new term ideal gas. The meaning of the ideal gas has to be clearly specified in relationship to our systems and its environment. But let's see if we can solve this problem for whatever we have learned so far. Now we have an ideal gas in a piston and cylinder assembly. There is no mass flow in and out of this system. But what is my system? I will select the gas confined in the cylinder as my system. I put dotted lines to remind me that this is my system. It is just the gas that is confined in this piston and cylinder assembly. I'm going to compress this gas from V1 to a new volume of V2, and I would like to find out how much work do I need to do to compress this gas. And of course I need to find out what is my final pressure. Now I said that this is going to be an example on an ideal gas. Now let's find out what is an ideal gas. Ideal gas obeys the ideal gas law. Ideal gas law is not a law, it is an equation of state. Through ideal gas equation, we can determine the state of a system that has the characteristics of the ideal gas. What are those characteristics? What makes a gas an ideal gas? What makes a gas an ideal gas are two assumptions. Now let me write on the side of the board. That in order for a gas to behave like an ideal gas, to follow that relationship, it has to have following characteristics. Number one, there should be no interactions between the molecules. And also, the volume of the molecules in comparison to the total volume that the gas occupies is negligible. With that, we obtain a relationship of P times V is equal to N times R times T. And at the end of this example, I will also show you how this relationship is originally obtained. Now, this is one relationship about an ideal gas. The other relationship relates the ideal gas internal energy to its temperature. Here, the ideal gas law or equation of state relates P times V to the temperature of the ideal gas. There's another relationship that relates the internal energy of an ideal gas to its temperature. The internal energy of an ideal gas depends only on temperature. So these are two characteristic equations that specifies what an ideal gas is, and this is, despite it's an approximation, is a very good approximation that helps us solve a lot of problems that involve ideal gases. Now let's see, with these two pieces of information, if I can use these equations to solve this problem and come up with an answer. Now, this T and this T are not the same T. Remember, this is temperature, this is time. So let me see. This example has a heading that it is an isothermal compression. Isothermal means temperature is constant. So let's write it here to add to our vocabulary. Isothermal. T is constant. In other words, dt over dt is equal to 0. It doesn't change with respect to time. I will add few more isos. Isobaric, P is constant. In other words, dp over dt is 0. And isochoric, volume is constant. dv over dt is equal to 0. Okay. T is constant. Let's just take these two pieces of information. Internal energy of an ideal gas is only a function of temperature, and our temperature is constant. Let's combine to obtain du is equal to Cv star dt. All right. The richness in the symbolism of this constant will become apparent as we go further and further in the course. Of course, I can divide both sides by dt. This is an isothermal process. Isothermal means temperature is constant. Its time derivative is 0. Its time derivative 0. This is 0. Therefore, du over dt term is 0. du over dt term is 0. So I start by writing 0. The system is closed. There is no mass in or out. For closed systems, m is constant. M dot I is equal to 0. All of them. This is 0. This term drops out. This is 0. This term drops out. There's no shaft work. I don't see any impeller. I don't see any impeller in this configuration. There's no shaft work. I have minus P dV over dt. Okay? Minus P dV over dt. And in order to have a meaningful equation, I have to have Q dot. There is another reason that I need to have Q dot. From a mathematical perspective, in order for this thing not to be equal to 0, I have to have something, right? The only choice I have is Q dot. On the other hand, I know something else, that in order to maintain the system at constant internal energy, when I compress this gas, I do work on this gas. The energy of the gas increases. And the energy of the gas is proportional to its temperature. If temperature is constant, its internal energy is constant. In order to maintain the internal energy constant, I have to remove heat. So I just have arrived at a very important conclusion, that when I do work on a gas under isothermal conditions, in order to keep the temperature constant, I have to remove energy by some means, and in this situation it is heat. Q dot is going to be equal to minus P dV over dt. Now what will I do? I will rearrange. Q dot dt. This is the instantaneous heat flux. Of course, when this goes to the other side, the minus sign disappears. Or I take this one to the other side. Q dot dt is equal to integral P times dV. Now what will I do? I will use the equation of state to relate P, V, and T to one another. I will substitute this as N R T over V from this equation. But N is constant, mass is constant, moles are constant. R is the universal gas constant by definition. Temperature is constant. So I have on this side Q, this dot per time cancels with this T through integration. Q is equal to, let's move it down a little bit so that we have a meaningful space. Okay, Q is equal to nRT integral from V1 to V2 dV over V. And that is equal to nRT ln V2 over V1. V2 is smaller than V1. This group is less than 1. This is going to be negative. Q is going to be negative. And when we have negative Q, it means that it is leaving the system boundaries. Negative Q means that heat is leaving through the system boundaries. But we were after work. Well, work is this term. This term is work. Okay? So now we solve this problem. This is minus nRT ln V2 over V1. Work done on an ideal gas under isothermal conditions. Now, through this example, what have we learned? Number one, we have learned that the ideal gas law from this point on is an equation of state, is an equation that allows me to determine the state of a system. Number two, internal energy of a gas is only of an ideal gas. Internal energy of an ideal gas is only a function of temperature, and that functionality has a proportionality constant of Cv star. This is the heat capacity at constant volume, and why we call it constant volume will be more clear in few lectures after this. The star indicates that it is for the ideal gas. In other words, we now know that the heat capacity for a real gas can be different from the heat capacity of an ideal gas. Then we have learned conditions of isothermality, isobaric and isochoric situations. Then we learned the assumptions of the ideal gas, that the ideal gases have negligible interactions between the molecules, that the molecules do not attract or repel each other, that they bounce off each other through elastic collisions, and that the volume of the molecules is negligible. Now, I will clean the board and I will make this point a little bit more clear. Now, let's see where this equation came from. In the early days, that people were curious about converting thermal energy into work, that experiments have been conducted that they were trying to relate pressure, temperature, and then they realized that the number of moles is a parameter, and so on and so forth. Of course, the concept of pressure is relatively new in the light of human evolution. So now, after making thorough experiments using different gases, performing these experiments at different temperatures, the groups working on these problems realized that when they plotted a PV function as a function of temperature for all of the gases after a certain temperature, all the data fell onto the same line, whether they had nitrogen, oxygen, carbon dioxide, whichever gas that is used, that all of the data has fallen to a straight line. So they have calculated the slope, and they realized that the slope is constant regardless of the gas, but is proportional to the number of moles of the gas within the system. The curiosity continued, and they decided to extrapolate. All right? Extrapolation is extension of the function beyond the data measured domain. Okay? So what I did here is extrapolation. When this data was extrapolated, the intercept turned out to be minus 273 degrees Celsius. So this point is the point that we call absolute zero. the opposite term of absolute is relative. So Celsius is a relative temperature. It is a relative scale chosen because of the convenience between the freezing and boiling points of water at atmospheric pressure. But absolute zero is absolute. Nothing exists beyond that. So this absolute zero is one of the fundamental ground rules of our abilities of making energy estimations. So this is our absolute reference frame. This is something that we have to remember. Absolute zero is also a reference plane. All right? We start making all our measurements from absolute zero. It's a reference plane. So, now when our system in reality, if we take an ideal behaving gas and cool it, first the gas has to become a vapor. The vapor has its liquid, that is it in equilibrium with. So we have to have a condensation, and these condensed molecules occupy a space. If we take those liquid molecules and cool it, we will freeze it. But the liquid and solid are not going to change too much in terms of the occupied volume. In other words, volume of the liquids and volume of the solids are not too different from one another, unless we have some extreme situation. But we have a finite volume. When we cool a gas, when we liquefy, we have a finite volume. All right? But here, when we take this one and extrapolate and obtain our absolute zero, we neglect the volume of finite volume of these molecules. The ones that we could condense, the ones that we could solidify. Okay? And of course, the second assumption that makes this relationship linear is the absence of interactions between the molecules, so that when we compress the gas, molecules continue to make elastic collisions amongst themselves. Okay? If they attract or repel each other, the final pressure should be different from what we obtain from this equation. So this is a general summary of what ideal gas law is and how it somehow diverges from the reality. In the meantime, we have learned a new concept of extrapolation. It is important in science and in engineering. And there is one more thing that is called interpolation. Interpolation is between the data. So we will do interpolations to find values between two data points. It means just we take two measurements and we impose a functional dependency on those two measurements, whether it is linear, quadratic, or whatever, and then we use that function to estimate the values in between. So within this frame, we have learned the assumptions of the ideal gas law based on some experimental measurements. We have learned an absolute scale, absolute zero, which is our now reference plane. and we have learned terms, interpolate and extrapolate.